Okay, guys, hey, welcome to chapter 6. So in this chapter, we're actually going to build off some of the ideas in chapter 5 with probability, which is sort of exciting, but in a kind of a more realistic sense, at least in my opinion. And so I'm excited to kind of jump into it. First thing you want to do, though, is you want to download these notes. This is the 6.1. Now, there's two 6.1 notes, and I didn't label them day 1 or day 2. This is the mean and standard deviation of section 6.1, so make sure you do that on Schoology. But with that being said, let's jump into a couple things. So back in chapter 5, we learned about a probability model. We said, probability model describes the possible outcomes for a chance process and the likelihood that those outcomes will occur. So one of the common ones we looked at was flipping a coin. And so let's imagine we flip a coin 3 times, and we'll define X as the number of heads obtained. So if we were to list out our sample space for that particular event, or that particular scenario, I should say, it's not an event necessarily, we could find the following happen. Now you'll see, okay, we could flip 3 tails in a row, or we could flip 3 heads in a row. That would be X equals 3. Of course, we have all the different combinations of where we get heads once or heads twice, and keep in mind that those combinations are different depending on what order they occur in. So heads, tails, tails is different than tails, heads, tails, even though you get the same number of heads and tails in those two situations. We could also list that in a table where we have our events across the top, and then right below them are the probabilities associated with those particular events. And then, of course, last but not least, since we have talked about graphs, you can look here. Here's a histogram. This histogram, you'll notice at the bottom, is not made of bins. It's actually made of sort of discrete values, 0, 1, 2, and 3, so not intervals. And the bars are connected, but each of these bars represents that probability, and on that y-axis you can see that probability there. So a bunch of different ways for us to talk about and represent that scenario. So, all right, let's define a couple other things. In this chapter, the big thing we're going to talk about is random variables. And a random variable, all right, we'll take some numerical value that describes the outcome of some chance process. The probability distribution, which we've been looking at with the problem above, all right, of a random variable, gives all the possible values and their probabilities. Okay. So there are actually 2 main types, and I mentioned one of them I kind of talked about with the histogram, but the 2 main types of random variables that we're going to look at are discrete and continuous. Now, the difference between them, discrete and continuous represent 2 very different things, and you may have heard these in other math classes or maybe a science class, but essentially discrete is counting numbers. So, for example, in real life, I consider shoe size to be a discrete random variable, because if you walk into a shoe store, you're like, well, I wear a 10, or I wear a 10 and a half, or 11. You would never walk in and say, I wear a 10.762 shoe. So in other words, shoe size is not like on a continuous scale. It's very discrete by nature. The number of siblings that I have is discrete. I have 1 or 2 or 3 or maybe more or less, right? Depending on your family. Continuous, on the other hand, is sort of like a spectrum. Time is a very easy continuous and familiar continuous variable. Since every moment of our lifetime is continuing to move, we never really have a moment where it stops. We consider that to be continuous. So we're going to start with discrete, because discrete tend to be a little bit simpler. Right? You'll see when we get to continuous, hopefully tomorrow / maybe Thursday. Or I'm sorry, Friday. So a discrete random variable takes a fixed set of outcomes with gaps in between them, right? We don't have sort of a scale or a continuum. There's just 1, 2, 3, or whatever they might be. The distribution of the discrete random variable lists all those values. So just like the table above, we've got what the outcomes can be. And by the way, looking at the flipping a coin 3 times, that's a very discrete situation too, right? You can't flip a head 2.5 times. So up here, you see all the values, and then right underneath them, you see all the probabilities associated with those particular events, so that we can see how likely or unlikely they are to occur. Right, so every probability has to be a number between 0 and 1, just like in Chapter 5. And if it's a good or a legitimate probability model, all of the probabilities need to add to 1. All right, so let's take a look at one here together. So let's imagine selecting a U.S. high school student at random. We'll let X be the number of languages spoken by that particular student. Okay, the table below shows the probability distribution based on the number of students from the U.S. Census at School database. So we had 63% of students pretty much speaking one language, but 29.5% speaking two, and then we had a few speaking three, very little speaking four, and almost nobody, maybe one person speaking 5 languages. All right, so the first thing we want to do is we want to show that this is a legitimate probability model. So we'll come over here and we'll make sure that we just add all these up. 0.65 plus 0.008 plus 0.002 equals, and sure enough, if we grab our calculator, these add up to 1, which makes it a legit probability model. Just like I said back in Chapter 5 with a few things, we'll create some of these probability models ourselves, and there'll be some rounding that's involved when creating them. So if you do end up creating your own and rounding, and then you start adding them up to check that it's legit, you might get something that's a little bit below or even above 1. So 0.9999 or 0.9998, and we pretty much say like, okay, that's fine. It's just, we'll chalk that up to rounding. So just keep that in mind as we move forward in this chapter too. All right, let's go ahead and create a distribution. And we didn't leave much space down here, so I apologize, but let's go ahead and get on the bottom our number of languages. 2, 3, 4, 5, and we'll say this is languages. And then up here we've got probability. I'll just abbreviate probability. And it looks like the highest probability we need to get to, according to our table, is 0.63. So we should be able to count, I suppose, by tens or 0.1s. All right, so yeah, that'll get us to 0.7 at the top. And now we can graph these. So let's first start with 63%. So we'll draw a line over. Unfortunately, on this, I can't make straight lines like I can in Notability, so you guys will probably have an easier time than me. 0.295, which is essentially 30, so I'm just going to go ahead and put a line there at 30. And then we've got about 6.5%, so I'll come down here to where about 6.5% right there. And then we're way down there. We're not quite even at 1, so I'm going to zoom in here quite a bit and try to get some indication that there's some probability here, and then even less over here. I feel like this one should just kind of touch the line down there. So let me kind of make these a little bit thicker there. All right, so there we go. Yeah, we've got our nice probability model. Obviously, this is skewed right. We can talk about the shape again this time because it's quantitative. So yeah, we've got a skewed right distribution, and obviously languages then drop off, or the percentage of people that know a ton of languages drop off as we talk about more and more languages. All right, so now we can actually talk about some probabilities. So what's the probability that a randomly selected student speaks at least 3 languages? So we'll turn back to our probability notation that we learned in Chapter 5, and that'll stay with us pretty much until the end of the year, but definitely through this chapter. So in this case, at least 3 would be anything greater than or equal to 3. And we'd come up here and we'd say, okay, well, we're looking for these 3 numbers right here. So 0.065 plus 0.008 plus 0.002, and that all equals 0.075. And there we go. All right, show your work, get your notation, circle your answer, and then if you're asked to interpret. But we're not on this problem. We'll do an interpretation below. All right, so let's imagine the University of Kentucky posts the grade distribution for its online course. Students in Statistics 101 in a recent semester, 26% of them received an A, 42% received a B, and 20% received a C, 10 D, and 2 Fs. So choose a statistics student at random, and the student's grade on a 4-point scale, we'll let F be 0 and A be 4, is the discrete random variable. So we'll come over here and we'll say, okay, 0, 1, 2, 3, and 4. These will be our grades. All right, let's label these. It looks like 2%, 10%, 20%, 42%, and 26%. So B is clearly the most earned. Let me fix that 6 there. The most earned grade here. There we go. All right. So in the first problem, we want to find the probability, but we also want to just interpret what does it mean for p to be greater than 3? What does that exactly mean in words, right? Well, if we look at that, that means that it's got to be greater than 3, so they have to earn a 4. That's the only possible thing here, and a 4 represents an A in this situation. So we would say, well, this is the probability that a randomly selected student in statistics, I'll just put stats 101, earned an A, right? That's what we're looking at. What's the probability that they earned an A? So down here we'd say, well, that's pretty easy because obviously our table kind of gives us that value. That probability is 26%. There you go. Okay, what if we say, and switch it up a little bit, what's the probability then that they, it's greater than or equal to 3? All right, so just putting an equal to sign on that inequality now obviously changes the situation for us. This time we are allowed to include a B. So it's whether the person earned an A or a B. So the probability, and let's just abbreviate this one so we don't have to be as specific. The probability of earning, we'll just shorthand this one, in A or B. Okay. Now, obviously, we'll test quiz and things. We want to be as specific as we were in part B on part C. But for now, we'll skip it. All right, so a couple things. Let's find this probability, and I'm going to show you some notation that's not required, but you may see it on free responses and multiple choice questions, things like that. And I just don't want it to be something that catches you off guard because we've never seen it in the notes. So obviously, if we want to calculate this, we're going to add up these two numbers, 0.42 and 0.26. But before we just add them up, the notation that you will sometimes see is people will say, okay, well, you have to add up the probability for 3 and the probability for 4. So really what you're doing is you're saying, okay, look, I'm going to take that probability for 3 and add it to that probability of 4. And they'll use this middle step to kind of indicate what they're going to do in their notation. Right? So just something to keep in mind that you might run across. Again, not, in my opinion, required, but certainly something that you just, like I said, don't want to get caught off guard by later on. And I believe, what do we have here? 68%. There you go. And so 68% chance that, if we randomly selected a student, that they earned an A or a B. Okay? All right, let's write the event. The student got a grade worse than a C in terms of random variable. What is that probability? Well, worse than a C is a D or an F, so it's either 0 or 1. So we actually have two different ways we can write this. We can say, okay, what's the probability that it's less than 2? Right? Not including 2, not including a C. So less than 2, a D or an F. Or what's the probability that it is less than or equal to 1? All right, so either of those notations would actually work and be correct on this particular one. But again, no matter what we do, and I'll just use this notation again, we're going to take the probability of 0 and we're going to add it to the probability that x equals 1, which in this case would be 0.02 plus 0.10 equals 12%. So we've got a 12% probability of that happening, that a randomly selected student earned a D or an F. Okay. All right, so a little bit on just simple calculations, what those interpretations mean. All right, so let's hop to the next page here then. And this is where I think things get a little bit interesting with discrete random variables and a little bit more applicable when it comes to our lives. So when analyzing, we're going to talk about the mean and the expected value. When analyzing discrete random variables, we follow the same strategy we did with quantitative data back in chapter 1 and 2 and even 3. We describe the shape, the center, the spread, and we identify any outliers. So essentially we're talking about socks back from chapter 1. So the mean, let's talk about that first, which will be the center of any discrete random variable, is an average of all the possible outcomes, just like it is with any average that we've ever worked with, except each outcome, okay, is weighted by its probability. Obviously, when we think about mean, we think about just adding up all the numbers and dividing by however many there are, right? But all of those numbers are just sort of equally likely, equally weighted. In this particular case, some of my outcomes are more likely to occur than others. Go back to the first page real quick. you were more likely to get 2 heads or 1 head, it was like a 3/8 probability, than you were to get all 3 heads in a row. So since each of those probabilities has a greater or lesser chance of occurring, we need to make sure that when we're averaging, we're including the fact that that's the case. So let's imagine we have, and let's look at this green box here, we have a random variable whose probability distribution is the following. We've got our values, what can occur in this situation, and the probabilities associated with them. But again, each of those probabilities is a little bit different, making those outcomes a little bit less or more likely to occur. So when I go to find the mean, check out our notation real quick, just a tangent for a moment, back to mu, the symbol for mean, and then we use sub x to represent, hey, it's the mean of this discrete random variable x. Okay. I don't really see this one too much. It's just the expected value of my expected value of my random variable. But check this out. Here's how we calculate it. It's my value times its probability plus the next value times its probability plus the next value times its probability. Notice that we're not really going to divide at the end by anything because all of those probabilities are technically fractions and we're sort of dividing at the beginning anyway. And since they're all from the same sample space, they should all, I suppose, theoretically be over the same denominator. So yeah, it's kind of built into the problem that division is that we often see with normal mean calculations. Our shorthand notation is just the summation, that capital sigma, of all of our x values times all of their probabilities added together, okay? By the way, this is found on the formula sheet. So if everything, I'll say this, guys, it was a recent change. I believe last year was the first year when it comes to both discrete and continuous. Most of the formulas out of this chapter are on the formula sheet. That used to not be the case with continuous, but it's recently changed, so it's good news. Okay, so let's look at this. I love expected values and aka means with discrete variables because we see it so much in real life. And I think the most common place that we get fooled, because I'll be honest with you, a lot of people just don't understand expected value and how it works and why they're at a disadvantage most of the time in life with a lot of things that they do. But I think casinos really kind of, or just like gambling in general, really give us an idea of how everything is sort of rigged for us. So essentially, people who understood expected value better than other people designed ways, right, to take advantage of it. And casinos were a great way for people to do that. So we designed these, they designed these games in which they always had a slight advantage. So let's look at one, okay? Suppose the person is playing roulette. There are 38 slots on the roulette wheel. 18 of them are red, 18 are black, and then there are 2 green. And if you're not familiar with roulette, it's a wheel. You've got red and black and then those 2 green slots, and you spin it, and there's a ball that's bouncing around in there, and then that ball will land in either a red, black, or green spot. Obviously, if it lands in green, you're going to get a sort of a bigger payout, I suppose, but most people don't bet on that because there's only 2 out of 38 slots. So let's say a person bets $1 on red, just $1. If the ball lands on red, they win, right? So what they'll do is they'll get their original $1 back, and then they'll get another $1 on top of that. So they've netted $1, if you will, right? If it lands on black or green, though, the one they didn't bet on, they will lose that $1, so they've netted negative $1. Let's define x as that net gain. Now, that's important right here real quick to notice that x is not the amount of money you're getting back, because some people might argue if you win, like, oh, you got $2 back, you got the $1 you spent plus the other $1, right? And that's not necessarily the case, okay? So here's what we're going to do. Let's come up with the probability distribution for this particular thing. Guys, I want you to kind of keep in mind, and we'll talk about this, that as we're making this, let's make a table here. This is so interesting because, and you'll see what this number comes out to here in a minute and why it's a situation, but it's just so important that we understand how expected value works, so that we know we're not sort of being taken advantage of, if you will. All right, so let's label these. This will be our values. This will be our probabilities. I usually like to make all my tables in the same sort of format. Values up top, probabilities in the bottom. Okay, so we've got 2 situations here in terms of our random variable, which is how much we net. The one situation is we net negative $1. Like we lose, we land on black or green, and we're out, we lose our dollar. And I think I'll get to the probability here in a second. The other one is we gain $1. Even though we get our original dollar back, we only care about the net gain, so we actually get $1. All right, so let's talk about these probabilities then. So the first one, the losing $1, there are 38 slots, and there are 20 of them that would cause us to lose, the 18 black and the 2 green. So we've got a 20 out of 38 chance of landing in that spot. Whereas if we placed a bet on red, which we did in this case, there's only 18 red slots, so 18 out of 38. Now immediately you can see that you're at a disadvantage in this game. Some people, sort of are like, well, okay, whatever, I'll just take that disadvantage because I think, I'm feeling lucky today, I'm going to win. All right, and that might be true, right? But here's the thing about a casino. They don't count on you playing just a few times, right? They do everything in their power to sort of keep you around in that casino to keep going, okay? And play as long as you possibly can, and here's why. So Part B explains that exact situation. Why do they want to keep you there so long? So what is the player's average gain, aka expected value? Remember, this is not the expected value gain on a single bet, but it's the expected value over many, many, many bets. All right, so what we'll do is we'll say, okay, well, we'll take our mean of X, and let's take negative $1 times its weighted probability of 20 over 38, and we'll add that to our other gain of $1 of 18 over 38. And there we go. All right, so we'll plug this in our calculator here, and I'm getting about negative 0.05. So, guys, we are expected to lose 5 cents every single time we play this game. Now, again, you might be like, that's not a big deal. I could play it a couple times and be fine, right? And you're right, that's not too bad. But think about, okay, you play it a couple times and lose, but then they've got hundreds or thousands of other people playing it a couple times and losing, and this starts to add up really, really fast. Plus, they know from time to time you're going to win big, but if they can keep you going, they know in the long run, they're going to gain 5 cents every single time you put money on that table, right? That's the expected value. And they have made a fortune off of this idea. And people get fooled by it so easily because they're like, well, every time I go to the casino, I walk out of there with a bunch of money. And that's also another thing called an availability bias. They don't often recall the number of times they lost money. They only remember the times they won money, but I'm not going to get into that today. I just think it's super interesting that we only want to see what benefited us sometimes. But anyway, my point being, we actually lose money on average every single time we play. So let's interpret this. This essentially means after many plays, we are expected, on average, to lose 5 cents each play. And there it is. All right? And they count on this happening. In fact, they don't even count on it. They know it's happening, right? It's mathematics, and it's true, and this is the case, right? And so that's why casinos never have to worry. You're always like, aren't they afraid that a ton of people are going to come in there and win a ton of money and then just like bankrupt them? No, not really. So it's interesting. So common error real quick. Guys, 5 cents is not something that we can actually lose on a game to game. And so a lot of students believe that their expected value is wrong because it has to be one of the values in their table. Like, oh, my expected value has to be lose $1 or gain $1. But remember, this is not the case, right? It's expected in that last example here that we just did to lose 5 cents, even though this wasn't a possible gain or loss on a single bet. So just keep that in mind. All right, so let's look at a couple things here to wrap things up today. Let's look at, I just want to do one more problem. Well, kind of two more here. I want to kind of look at the expected value for the number of languages here. So back to the language problem. Let's look at the mean of X, and let's 1, and let's get our... Take our, okay, there's a 63% of people so speak one language. So that's the chance of selecting a person. 29.5 speak 2 languages. 3, and then 4, and then 5. And I'm going to get, if we type this in, about 1.457. So yeah, not a table, or not a value we see in the table, but if we selected, right, if we selected many students, we would expect, on average, each student, sorry, I'm running out of room over here, to speak 1.457 languages. I'm sure you ran out of room too. Well, you guys have the ability to shrink, so if you want to kind of shrink that work, I don't have it on this app, so unfortunately I have to deal with it that way. But yeah, we expect them to speak about 1.457 languages. If we selected many, each one would speak about that. And I know that's not possible again, but that's the expectation, okay? All right, so let's look at one more, kind of get the probabilities associated with it, and we'll stop here after this one to get to standard deviation on Thursday. So let's imagine we have a multiple choice test. And we kind of talked about this back in the last chapter about like what's the probability of guessing correctly on all of the AP. I'm sorry, not AP, on the ACT, what's in the math section, and we did, so okay, there's 60 questions and each one has 4 choices, so that's 1/4 to the 60th power. But we never asked the question, what's the probability of like guessing correctly on 50 and then getting like 10 of them wrong? Right, and that question never really came up because, and to be honest with you guys, we didn't know the answer to that question, right, at the moment. We still don't, but that's what we're going to focus on a little bit in this chapter. So let's take a look at our first introduction into this idea. And I'm not going to dive into it too much because the idea that I'm going to talk about here is actually set for another section, but I do want to introduce it, all right, just to have it kind of in the back of our mind as we move forward. It'll pay off later. So each of these multiple choice questions, A through D, it's a 5-question test, so four choices, 25% chance on each one of getting it correct, and a student blindly guesses on each item from 0 to 5. Let's let X be the number that are correct. Now, a little while ago, we said, we know this one. This is, okay, there's a 25% chance of guessing any question, and I need to get all 5 of them correct. So this was something that we saw back in Chapter 5. Each question's independent, so we just multiply those probabilities together, or AKA take it to the 5th power. That's going to be 0.00098, so really low chance of getting that. On the other hand, we also know how to find it for 0. If you're getting 0, correct, you think about it, you're like, well, you're not going to take 0.25 to the 0th power. Or we're getting these questions incorrect, and each question actually has a 75% chance of getting it incorrect. You actually have a greater chance of getting it incorrect, right? So if we want to get 0 of them incorrect, we say, well, you've got a 0.75% chance of getting them incorrect, and we want to get all 5 of them that way. So 0.75 to the 5th power, which is a 23.7% chance. So actually much more likely, right, to have that be the case. And this leads to an interesting idea if you look at these two sort of boundary probabilities that we talked about in Chapter 5. You have a 25% chance of getting it correct. You have a 75% chance of not getting it correct. So then that begs the question, what's the probability then of getting one question correct? Or you say, okay, well, that means I can get one question correct, so 25% to the 1st power, but I got to get the other 4 incorrect, and there's a 75% chance of doing that. So this is sort of an intuitive calculation, and it actually is, it works, right? So we'd say, okay, well, let's see, 0.75 to the 4th power times 0.25, okay, and times 0.25, and we would get, let's see here, about like a 0.07, I guess, is what we would get. But here's the issue. That is not correct, right? The problem is when we think about getting one question correct, it's which question? Right? Because let's say I get the first one correct on accident, then I'm not allowed to get the other 4. But let's say I get the first one wrong and then the second one correct. That's different than the first situation I just talked about a moment ago. So no matter where you get that question correct is really, really important because it makes a big difference on what the order is and then when you're allowed to get it correct and when you're not. And so we've got all these different combinations of ways we can do it, and that brings in an idea from probability, which is combinations. Guys, combinations are the number of ways that things can occur. If I want to get one question right, how many ways can that happen? And you think, well, if you think it through this logically, you're like, I think it can happen 5 different ways. Either you can get the first one right, the second one right, the third one right, the fourth one right, or the fifth one right. That, it's just one of them. And you're right, there's 5 different ways. And so essentially, we want to multiply by all 5 of those different ways. We want to see this thing happen 5 different times. And if you take that 0.079 and you multiply it by 5, you get, let me do that one more time here, 0.079 times 5, you get about a 39.6% chance, which is exactly what happens here. Okay, now, here's the problem. To come up with those 5 different ways, it's pretty easy to do when it's just choosing, you're allowed to get one correct, but what if it's 2 correct, which we're going to do on the next example? Then you're like, well, I guess you can get the first and second one right, and then you can get the first and third one right, and then you can get the first and fourth one right, and then you can get the first and fifth one right, and then you have to go back and you have to start over again. So I want to introduce you guys into combinations here. 5 choose 1. Okay, that's 5 choose 1. By the way, if you want to get a combination in your calculator, you'll go to the math key and then over to probability when the math key, and you'll see NCR as your option number 3. That is combination, and so you would type a 5 in, and then you would type a 1 in into your 2 spots, 5 choose 1, and you'll notice when you hit enter, you get 5. Your calculator is saying, hey, look, if you've got 5 things and you want to get one of them, there's 5 different ways to do that, which we kind of thought through. But again, when we come over here to getting 2 correct, well, let's do this first. Okay, 25% chance, we want to get 2 of them. 75% chance, we want to get 3 of them wrong, right? But we have to do this a bunch of different ways. Instead of using our fingers or our mind to kind of count the different number of ways we can get 2 correct out of 5, we can use our calculator to do 5 choose 2 for us out front. So 5 choose 2, if you go to math and you go over to probability, say, okay, well, 5 and 2, that's 10 different ways. This number is actually a 10, much bigger number than what we saw a second ago. So let's take this calculation, then let's take 10 times 0.25 to the second power times 0.75 to the third power, and we'll get about, let's see here, whoops, I typoed something. I got about 26.4. So about a 26.4% chance of getting 2 out of the 5 correct. You'll notice that number dropped off. It seems like maybe 1 out of 5 is the most likely situation. Let's do this one. We want to get 3 correct this time, so 25 to the third power, and then we want 75% chance. We want 2 of those. And this time we'll do 5 choose 3 out front. And we kind of see how this is now working, and then the next one we do 5 choose 4. The reason we don't have to do a combination out here, I mean, you guys can do 5 choose 0 out front if you want, but that can only occur one way when you get them all wrong. So we don't really ever need to do 5 choose 0 or 5 choose 5. If you're like, hey, I have 5 things and I want to choose all 5 of them, how many ways can I do that? You'd be like, one way, right? You think about it, you're like, you can only choose 5 of them one way. So we never have to do 5 choose 0 or 5 choose 1 on any of these. I should have put 5 choose 5 right here. And then 5 choose 0 over here. But yeah, so that's kind of what's happening. Okay, so I erased this line that I somehow put in there. Let's get these 2 calculations here, because again, we'll focus more on this idea later in the chapter, but for now, we just want to get these probabilities and talk about these problems here. So this is 0.088, and this is let me fix that 8. 0.088 and 0.015. All right. So yeah, look at that. It's actually, you're most likely to get 1 out of 5 questions correctly, even more than getting it incorrect. So verify that it's a legit probability model. So we'll add all these up, and this is where we're going to run into that situation where we kind of have a rounding, error. All right. And I get over 1 in this. Oops, I missed 1. I get like 1.00098. So yeah, a little bit over, but Still a valid probability model. And now we can just go ahead and find all of these different probabilities. What's the probability of getting x equals 2 or x equals 3? We'd say, 26.4 plus about an 8.8% chance. That's going to be about 35.2. What's the probability of getting something greater than 3? Then in this case, we're adding up the 4 and the 5. And that's going to be 0.01598. And then what's the probability of getting at least one correct? So 1 or more. Two ways to do this. You can either add up all the ones above 1 and above, or you could just, in my opinion, you could just take 100% and subtract 0 out, which I think is a much better route to take. Remember, that kind of goes back to the at least rule from the chapter 5, which is like 1 minus the complement of the event, like it not happening, which in this case would be if I got 0 correct. So this would be about 0.763, right? So that's our probability. Okay, and we'll stop there, guys, because we're going to pick back up on standard deviation. But hopefully that gives you a little bit of an intro into random variables, how to get the expected value, and then, of course, maybe a little intro into how to calculate those probabilities for a variable. So cool. If you have any questions, let me know over email. Otherwise, I'll see you guys tomorrow. Have a good day.